Hello everyone, welcome. For this exercise, we are asked to find a power series expansion about x equals 0 for a general solution to the given differential equation y prime minus 2xy is equal to 0. When we're presented with this type of problem, the first step is to assume a solution in the form of a power series. We assume that the solution y is an infinite sum of terms starting from n equals 0, and each term has the form an times x to the n, where x is our independent variable and an is a constant. Next, we need to plug this solution back into our differential equation, and we see that we not only need y, we also need y prime, or the derivative of y. So we could take the first derivative of our assumed solution form as such, and we end up with y prime is equal to the infinite sum of n times an times x to the n minus 1 power. Also, it's important to remember that the starting point of the summation on y prime, which is highlighted here in red, has changed from n equals 0 to n equals 1. This is because taking the derivative of y eliminates the first term, since it is just a constant. Therefore, we begin our summation with n equals 1 for y prime. We can now plug y and y prime back into our original ordinary differential equation, and we obtain the following. What we can do next is take the x factor in front of the second summation and allow it to absorb into the infinite sum as such, which we could just write as x to the n plus 1 power. At this point, we need to focus on the exponents on the x's. We see that we have two different exponents, x raised to the n minus 1 and x raised to the n plus 1. The objective here is to transform these summations such that the exponents on the x are the same. The reason for this is because we need to equate coefficients later in the problem, and having the same exponents on x will allow us to do this. The way this is done is simple. All we have to understand is that we are allowed to shift the n's in a summation as long as we shift the starting point of the summation in the opposite direction. So, if we want an exponent of n on the x in the first summation, we need to shift n forward, which is not a problem as long as we shift the starting point backwards. The same can be applied for the second summation. If we want an exponent of n on the x, we need to shift n backwards, which is not a problem as long as we shift the starting point forward. For the first summation, this is done as such. We simply add 1 to the n's in the summation, and we subtract 1 from the starting point of the summation. This results in x raised to the nth power. We can do the same for the next summation. We can subtract 1 from the n's in the summation, and we add 1 to the starting point of the summation, and we end up with the following result. Here we see we have x raised to the nth power for both summations, but there is still one more issue. We need the summations to have the same starting point. This again will help us later in the problem when we equate coefficients. We can accomplish this easily by simply writing out the first term for the first summation, which forces the first summation to begin at n equals 1, just like the second summation. And we see now the starting point is the same for both summations. The n equals 0 term simply becomes a1. Next, since we have the same starting point for each summation, n equals 1, we can combine the two summations into a single summation as such. Next, we have a common factor of x to the n, which we can pull out as such. The next step would be to determine the values of the coefficients in our power series, and this is done by equating coefficients. We can first focus on the constants on both sides of the equation, which on the left-hand side is just a1, and on the right-hand side is just 0. We can equate both of these, and we see that a1 is simply equal to 0. Next, we could focus on the coefficients of x to the n, which on the left-hand side is everything in the summation multiplied by x to the n, and on the right-hand side, simply just 0, because there are no x to the n's on the right-hand side, which is the same as having 0 times x to the n on the right-hand side. Equating the x to the n coefficients results in the following. Now at this point, it's important to remind ourselves what our goal is and how what we've accomplished so far is going to help us reach our goal. What we need to remember is we know our solution form already since we chose it. Our solution is a power series of this form. Now, if we expand the power series for, let's say, 7 terms, we see that it is these coefficients which we are trying to solve for in order to specify our solution. And we see from our analysis thus far, we already have a value for a1, which is just 0, from our first equation. The remaining coefficients can be determined by the second equation. So how can we use the second equation to determine the rest of the coefficients? We can isolate a sub n plus 1 and plug in values for n to obtain relations for each of the remaining coefficients. We could pick a value for n. Let's pick n equals 1. Once we plug in n equals 1, we see that this leads to us obtaining a relation for a2. And we see that we end up with a sub 2 is equal to a sub 0, which means a sub 0 is an arbitrary constant, which makes sense since we would expect one integration constant arising since our original ODE was first order. We can plug this in for a sub 2. Next, we can choose the next value for n equals 2, and after the same type of computations, we obtain a3 is equal to 2/3 a1. And we see that we already have a relation for a1 that we could directly plug in. Since a1 is equal to 0, this means that a3 is also 0. Next, we could pick a new n. We will pick n equals 3, and after the same type of computations, we see that a4 is simply equal to 1/2 a2. And we see that we already have a relation for a2 that we could directly plug in. We know that a2 is equal to a0, which is our arbitrary constant. We can plug this into our series expansion and move on to choosing n equals 4. And going through the same process, this gives us a relation for a5. And we end up with a5 is equal to 2/5 a3. And we see that we already have a relation for a3 that we could directly plug in. Since a3 is 0, this means that a5 is also 0. We can then move on to selecting n equals 5 and going through the same process. And we see that we obtain a6 is equal to 1/3 a4. And we see that we already have a relation for a4 that we can directly plug in. We know that a4 is equal to 1/2 a0, which is our arbitrary constant. And we end up with a6 is equal to 1/6 a0. And we have essentially solved the problem, but sometimes we are asked to go a step further and find a general form of the solution in terms of n. So what we could do is we can reset our count, accounting for just the non-zero terms. We start from 0, and we could draw this out until n equals 3. And now what we can look for is a pattern between the value of n and the corresponding nth term. We see that by paying attention to only the power of the x's and comparing it to the n, here we added the x to the 0 power for the first term, which is just 1, we see that a pattern emerges. We see that x is always raised to the 2n power for each term. So we could begin generalizing the power series solution by writing x to the 2n, which will account for all x's raised to the powers. Next, we can pay attention to the denominator for each term, and with a little bit of intuition, we see that the denominator simply follows the pattern n factorial. We can add the n factorial to our general solution as such. Next, we can include the constant a0 in our general solution form, which does not depend on n, so it just remains as a0. And finally, we can write the sigma, which will start from n equals 0, and this is the final general form of the power series solution to the ordinary differential equation.